Hello. In today's lecture, we're going to be looking at tutorial 9, which is on projectile motion with drag. So in the previous two tutorials, we looked at systems with no friction. So the total energy remained the same over time. So now when we introduce friction, we're going to see that the total energy will actually go down. So the friction will remove energy from the system. Okay, so let's have a look at what the system looks like. So we're going to have some particle moving. Let's say it's falling, some particle falling. So in the tutorial, it's got a little story about a skydiver, but we can just imagine it as a particle falling down with some kind of frictional force. So we've got mg going down, and then the frictional force is proportional to the velocity. And the proportionality constant is given by k. So we've got kv. So if we imagine that there's some net force going down, F net, it's going to be mg minus k times v. Okay, so the net force is going down, decreasing the height. So if it's starting out, let's say that the ground is here, starting out at height y, y naught, then this y naught is the starting point. It's going to decrease until it hits the ground here. Okay, so we want to investigate the system. We want to see how does the velocity change over time, what's the maximum velocity, and how does the energy change with time. So we'll see that there's going to be energy loss due to this friction. We want to see what is the rate at which this energy is removed from the system. Okay, so the first thing we need to do is find the equations of motion so that we can then solve them. So we've got our F net there, so we can use Newton's second law to find the equations of motion. So F net is equal to ma. So my double dot is equal to mg minus ky dot. Okay, so y dot is the velocity, of course. So dividing through by m, we get y double dot is equal to g minus k over my dot. Okay, so we've got a linear second order differential equation, but now with this y dot term over here. Okay, so this is second order. As we've seen with tutorial 7 and 8, we would like to turn this into two first order differential equations. So we've already introduced that variable. So this variable v is going to take the place of y dot. So v dot is going to be g minus k over m v. And then y dot is v. Okay, so we have two first order differential equations that we can then solve using the Runge-Kutta method. So all the tutorials, so 7, 8, and 9, you have to use the Runge-Kutta method. So we have the two equations with the initial condition that y naught is h. Okay, so that's the initial height, and that should be specified by the user. And then v naught is 0. Okay, so they simply drop from rest at a height h. Okay, so that's pretty standard. We can solve these two first order equations given those initial conditions. Okay, so you've done that before. What we're going to do now is do a little bit of investigation into the system by looking at the energy conservation. So is the energy conserved? Well, we know that there's a frictional force, so no, the total energy is not conserved. and we would like to see what happens to the energy over time. Okay, so from these two equations, we can find V of t and Y of t. Okay, so solving equation 1, we're going to get a list of velocity values over time. And for equation 2, we're going to get a list of Y values over time. Okay, so given those two lists, we can then find the kinetic energy over time as well as the potential energy over time. So the kinetic energy K, that's going to be half m V of t squared. And the potential energy U, that's going to be mg y of t. Okay. Now, if we add these two together, we're going to get some energy of t. That's going to be half m v of t squared plus mg y of t. But this is now going to be time dependent. So in the previous two tutorials, each term individually was a function of time. But if we added them together, we got a constant. So here it's a bit different. Each of them individually depend on time, but if we add them to add the two together, the function still depends on time. So energy here depends on time. And in fact, it's a decreasing function. Okay, because of friction, giving us the energy loss. Because of energy loss due to the friction. Okay, so we would like to investigate the shape of this E of t. Does it go down? Does the energy decrease? Sorry. Does the energy decrease linearly? Does it decrease quadratically? Maybe exponentially? How does it actually decrease with time? So here, sorry. So if we imagine we've got our function E with t, maybe it looks something like this. Something like that. Maybe it's exponential. So we would like to determine the shape of this curve as well as the rate of energy dissipation. So if we think about the rate of change, we're looking at dE by dt. So that's the rate of energy dissipation. In other words, it's like the power. So that's going to be, so the power here is dE by dt, and it's the rate at which the energy decreases. Okay, so that's question 3. And then question 4 is the theoretical solution. So we can see from the equations of motion over here that we have a linear second-order differential equation, which means we can use those methods that we looked at in the previous chapter to solve this. So we can solve this equation using these initial conditions, and then from that, we got ourselves the theoretical solution. Okay, and then you can compare the two. So once you have the theoretical, you can check, is the energy loss linear or exponential? You can just look at the equations and see what that is. Okay, and then there's a little extra bit there on finding the terminal velocity. That was done in the previous class test. Okay, so you can just look at the working for that to see how you find the terminal velocity. Okay, and then there was an extra bit to find the time taken. So if you look at the terminal velocity plot, something like this. Okay, so it doesn't have to be exact, but maybe this point over here, that time t, that is the point at which the velocity stops increasing and ends up plateauing at that point. Okay, so it doesn't have to be too accurate, just a rough estimate from looking at the graph that you produced. Where does the velocity start to flatline? And then that's our terminal velocity there. Okay, so just by inspection, it doesn't have to be too precise. Okay, but you will see that there's a point at which it starts curving over to being flat. Okay, and then just make a note of that in your program, just like with a comment to say, at this point, the skydiver has reached terminal velocity, something like that. Okay, so that's it for tutorial 9. So that will be due, I think, later next week, I think it was, or it might be the week after. Okay, so please just check on the Learn page for the exact date. But tutorial 7, that's due this Friday. Tutorial 8 is due on the Monday. And then later on, tutorial 9. Yeah. But like I said last time, a lot of the actual coding is just a repeat from the previous tutorial. So the implementation of the Runge-Kutta method, that's the same for all of them, right? So the Runge-Kutta method is the same for all of the tutorials. All you need to do is change those functions. So here where I mentioned the two equations here, 1 and 2, these right-hand side, the right-hand side of equation 1 and the right-hand side of equation 2, that just changes from problem to problem. But the actual implementation and the actual coding, that's the same. Okay. So once you've done the one tutorial, you've got a very nice template for the other tutorials. Okay, so that's just a little bit of advice to help with your working. If you do have any questions on this, please just email me, or you can ask me on Wednesday during the tutorial period. Okay, so we'll go through all of this again. Okay, and then after that, we're going to be starting the new section on scalar fields and vector fields. So that will be the theoretical side that we need to go through before we look at electromagnetism. So electromagnetism has a lot of work on fields, and we need to understand them from a mathematical perspective before we look at the physics of the electric field and the magnetic field. Yeah, but we'll get into that properly next week, after we've done these 3 tutorials. Okay, so if you have any issues, please just let me know, and I can help you out. Okay, so I'll see you on Wednesday.